Welcome, everybody. Continue our exploration of Fall 21, Test 2. We're going to do a mechanism with Robinson annulation. Setting up, we always need to say which ones we're doing first and which ones second. And we got to figure out what happened here. Well, these are not nomenclature numbers. I just got to say that right off. I'm going to put numbers on here. I'm going to count from here. That's an alpha position. That alpha position number 3 doesn't get us anywhere. But if number 1 becomes a nucleophile, it can attack number 6 and make ring size 6. And number 1 has an ethyl on it. Number 2 has a carbonyl. 3 has an ethyl. 5 has an ethyl. And 5, wait, did I do that? 3, 5, look at that. What a silly person. 3, 4. 4 has an ethyl too. 5 has an ethyl. And 6 used to be a carbonyl. So job 1, generate nucleophile on the alpha position. There we go. There's an anion. Supposed to be an anion. Wow. Lone pair, minus charge. Here's some squawking noises in the background. I don't know how that's happening. Got an H. Sadly, that's a red bond. What can you do? Red bond's going to break and become a lone pair. Where? On the alpha position. Let's draw it. Blue in green. A wonderful song. Okay, there we go. And 3 has ethyl. 4 also has ethyl. 5, wow, we got ethyls everywhere. 6 is a carbonyl. What do we have here? We have water that we just made. We have a nucleophile that's going to attack our carbonyl. We're going to generate an O-, that's a base. Bases will react with acids. Water is an acid, and it's going to generate our catalyst back. And we're going to have the aldol reaction product shortly. Aldol reaction product looks just like this, except no pi bond yet, and an alcohol on 6. This is 6 right here. Want me to verify that for you? I won't do all the numbers. 6 and 1. There you go. And so let's draw the ring like we see it above. Oh, that's an ethyl I barely cut off up there, so I'm not too worried. That thing that looks like a methyl. There we go. There we go. Ethyl fest. That's an OH now. And it needs to become a alpha beta unsaturated ketone in this example. How does one do such a thing? Well, you need to remove a second alpha H because there's an H here that is not here. Got to go. You have to remember you just generated hydroxide in this mechanism as well, so that you can use it to take that alpha H, generate a pi, and hydroxide is the nucleophile, is a leaving group. Not a good one, but hey, we started with hydroxide. It's perfectly acceptable. You want to see hydroxide? It's an OH- with a meow. You don't have to show me that. Cat's back. And what else? That's it for that. We've got our alpha beta unsaturated ketone. alpha beta. Typical aldol. Labeling's not working here. Typical aldol condensation product. This was the ARP down here, aldol reaction product. This is the CP, aldol condensation product. You don't have to write any of those things. You don't have to write alpha and beta. You don't have to write ACP. You don't have to write ARP. Just give me mechanisms and intermediates and make me happy. There you go. This guy, an enamine, is a nucleophile. You see enamines from now on, you think of nucleophiles. And don't think of it like a normal nitrogen nucleophile. The N lone pair is not the nucleophile, although it gets the reaction started. The carbon isn't a nucleophile without that lone pair. But you got to you got to resonate down towards there, generate the C double N, and then this becomes a nucleophile that attacks the beta position. Resonate all the way. This is our second 1,4 of the day. 1,4 addition again. And we're generating that. That's it. End of that story. Why 3 points? I don't know. Oh, we're not there. That's why. Sometimes using point counts is usually if it's 3, there will be an intermediate and then another step. And yeah, we haven't generated a ketone. We've got an enolate. So let's draw our enolate, shall we? Enolate. With ethyls everywhere. Well, not quite. 4 out of 6 positions. And we've got our double bond to N with the, new bond here. I'm just going to copy the piece above it. I'm going to put it in blue. Nope. Double N. There you go. We're going to acid base using what acid to generate this here? Where does this H come from? That's right here. It comes from right here. The solvent is also a proton source. Carbonyls generated. Acid-base chemistry to the solvent. And you've generated this molecule. And we better be circling a big old R group here, or else we're going to waste a lot of time. None of this changes. And we're going to use water and sulfuric acid to do hydrolysis. We need an O on this carbon. That's definitely happening from water. First step. Second step, we're going to deprotonate that water. In anticipation of that, we're going to need sulfate ion, which we haven't made yet, but you guys do know sulfuric acid's a strong acid, right? That means there's always sulfate present. You put sulfuric acid in water, you know what you actually don't have? Sulfuric acid. It reacts with water and makes hydronium. So a lot of textbooks will go, if you're using sulfuric acid in water, you better use hydronium as your acid catalyst every time. I'm not big on that. I just like saving a little time. I can use sulfuric acid. And keeping in mind though, sulfate ion is present whenever you need it. Sulfate ion can take that H off of the oxonium that you just made. How do you know it's an oxonium? Well, there's oxygen making a third bond. Oxygen with 3 bonds is an oxonium. Oxoniums that have H's on them can be neutralized with any base. They're strong acids. All right, back to blue arrows here. we have R. We have R attached to, where is R? There we go. A C that goes to an ethyl and an N with 2 methyls and an OH that's new. First up, you're going to have to protonate the N to make it a better leaving group. So HO3SOH, which you actually made, and it was already there. First step is to protonate it to make a better leaving group. Second step, the sulfate ion that you're making here. Gonna grab the H off of the hydroxide, kick it in to make a carbonyl. And this thing's going to pick up a proton from sulfuric acid. So now I think we've balanced out our uses of sulfuric acid and sulfate ion. And continuing your blue arrows here. And that's that. That gets us to where we need to go. And yeah, you'll be seeing this kind of protocol on your test for sure. Generate do an aldol reaction to generate a alpha beta unsaturated ketone or aldehyde. Do a 1,4 addition, followed by hydrolysis if it was an enamine nucleophile. Enamine nucleophiles, every time they're used, you're going to follow it with a hydrolysis as we're getting our carbonyl back. This is the carbonyl that used to be the enamine here. All those carbons are here. Okay, and we'll come back. We're going to be doing F. This is a directed something. We're attacking a ketone, so it's a directed aldol condensation again.
Dr. Whitaker, do you think we'll have time to do number 5 in part 4, the retrosynthetic analysis?
I believe you both want that, so yes.
Okay.
Yeah, I think that's what both of you want me to do next.
Yeah.
All right, so we're gonna stop this one, come back and do it. And then we'll do a retro after that.